So, in the last class, we talked about the very first object detection architecture, right? So, we talked about RCNN and we talked about how it works. We talked about selective search, which is a segmentation algorithm, and how it works on how it finds out the similarities based on 4 different things in the image itself. Then we talked about how the whole RCNN architecture works, right? We had selective search here. So selective search gave us approximately 2000 images. We warped those images to form 227 cross 227 images, right? Once we have these size images, we pass them through a CNN network, most probably VGG16, but we remove the bottleneck features. Once we have that, we pass it through one SVM which calculates the class score, and other we have a regressor model. So regressor is basically used to add more accuracy to the coordinates, the XY bounding box coordinates, right? So that is the whole thing we had with RCNN. So let us talk about what are the problems we have with RCNN, right? So the cons of RCNN. So the first thing is it consumes a lot of time, right? We talked how to calculate the object or object detection for one image. It takes 46 seconds, which cannot be used in real time. Second, it also consumes a lot of storage and computation. Plus, it is also a multi-stage network. So why multi-stages? See, you have one stage of finding all the region proposals using selective search, right? You have one stage this, and here you have network to extract CNN features, and then finally you have one network which passes through this network to calculate the score and regression models. So these were some of the problems, and these are very important problems if you think about it. So we had to come up with something better. So the next solution that we came up with was fast RCNN. Alright, so fast RCNN basically it solves all the problems that we had with RCNN. So one of the problems that we had with RCNN was, once you do selective search, right, you get 2000 such images. So 2000 such region proposals you get. Once you have these 2000 region proposals, one by one each region proposal is passed through the CNN network. It is passed through a CNN network, then it is passed through SVM, and finally regression model. By the way, if we talked about SVM, and if you have k classes, the total number of classes that will be used in SVM will be k plus 1. The reason why plus 1 is so that it identifies background as well. Okay, so what happens is, if you have 2000 images, they will pass one by one to the CNN network. So you have first image going in, then you have the second region proposal going in, then you have the third region proposal going in, and so on, right? So you have this whole thing going for 2000 region proposals. So this is a big thing. If you spend most of your time, the image is the same, right? If you think about it, the image is same. You have the same image. If you remember, what was the last image? You had a horse here, and on top of that you had a man. Okay, so the image was the same, and they were just regions from the same image. So why pass the whole image, the parts of the whole image again and again and again? Because this will just increase our number of region proposals, our time, our computation, and everything. What if instead of passing all these parts of the image one by one, what if we pass the whole image together as one, and somehow once the features are extracted, can we get the region proposals then and there? So that is the whole concept about fast RCNN. Let me repeat again, in RCNN what was happening was, you were getting 2000 region proposals. If you remember what are region proposals are bounding boxes which correspond to a particular segmentation that you have gotten from selective search. So you have 2000 such region proposals, and once you have these region proposals, they are warped into 227 cross 227 and they are passed through the CNN network one by one. So you have the first one going in, you get the region, you get the score and everything, you say okay, this is a bounding box, this is a object or not. If this is an object, we require this, so we keep this. Then the second one goes in, so second region proposal goes, same thing happens. Does it have an object, does this have a background, whatever, so you classify accordingly. Then the third one, fourth one, and this goes on till 2000 times. But if you think together, if you think it in a broader way, you will realize, okay, so what is happening is, even though these are region proposals, these region proposals are from the same image, right? So the whole image is the same, the region proposals are different, although they are all together add up to make one particular image. So what if instead of segmenting out these region proposals and passing them one by one, what if we pass the whole image together as one into the CNN network and then get the region proposals? Okay, so what we will go and understand about this deeper, but the whole concept, the whole problem that was happening is, you cannot pass 2000 region proposals because they all belong to the same image, so that will just be kind of a duplication thing. So that is what was causing a lot of problems with RCNN. So that is what was causing those 46 seconds. So they came up with the next solution, the fast RCNN. So as the name suggests, fast RCNN is obviously faster than RCNN. By the way, it is 146 times faster than RCNN. Now let us talk about the whole structure. So this is the structure of fast RCNN. You have the image, right? So this was the image I was talking about. So you have the human here, you have the horse here, okay? So they pass through a VGG16. Once you have the VGG16, you have all the features, alright? So you have all the feature maps and the features. Then you pass this image at the same time through a selective search. So this is here what is happening is, see, region proposal, example, selective search. So you have to propose the region, like we were saying, we were having region proposals. So to find the region proposals, we are still passing it through selective search. But what we are doing is, once we have the regions, once you have the regions, now we are placing these regions or finding these regions in the feature map itself, right? So this is what is happening. So the region proposals, once generated, they are projected on these feature maps, okay? So this is the whole thing. Now we'll talk about this, obviously we'll talk about what is happening, how it is happening, but let us go over this one by one, okay? So you have these two, suppose these two regions are there, they have been proposed from the selective search. Once you have these two regions, you have to project them onto the feature map. So this is my feature map, 60 40 512. This is the same thing, 60 40 512. Then you pass this through a ROI pooling, that is region of interest pooling. We'll talk about this also one by one. We'll go through everything, and then finally you have two fully connected layers of 4096 units, and they get divided themselves to two different fully connected layers, okay? So the very first thing, okay, everything aside, obviously these parts, ROI pooling and everything, we'll talk about that. The very first change that happens in fast RCNN is, it removes the SVM. So you do not have the SVM anymore. This time what you have a basic regression model, sorry, a basic classification model, my bad. So you have a basic classification model here, and that is being used to actually find out what class it belongs to. So you no longer have that SVM thing, and however the regression part still remains the same. So you have a regression model like you were having. So this is the very first difference, okay? So now let us understand one by one everything, okay? So you have the image. First, the image is passed through selective search. At the same time, it is passed through a pre-trained CNN network, okay? So VGG16, see, it is passed through VGG. So you have pre-trained, and this is backbone CNN. By the way, backbone CNN is basically CNN without the bottleneck. So these are just names, alright. So CNN minus bottleneck is backbone CNN. So you are passing this here, you find all the features. Once you have these features and you have the region proposals from selective search, you actually project these regions into your feature maps. Once you have those regions, now what you will do is, now you will directly pass the whole thing as once, alright. Okay, So that means what is happening is, now you do not have to, from the regions, you do not have to pass each and every region through your VGG. We are passing the whole image as once, and we are projecting the regions, and we are just projecting these regions, hence you do not have to pass this 2000 times. So the regions will not be passed through 2000 times. So that lessens your problem that you were having with RCNN. Alright, let us talk about this. So before we get into that, let me tell you something. Let us come across the term subsampling ratio. So what exactly is subsampling ratio? See, one thing that you need to know is, here you had an image, this was 600 cross 1000, alright, so 600,000. Now you got all your feature region proposals, right? All the selective search from here, you got all the bounding boxes. Now you have to project this into your feature maps that you got after passing the image. So these feature maps are of 60, 40 and 512. These are the dimensions. This is 600,003. Okay, so the dimensions are different. Hence, you cannot just put the values that were here. So suppose this was, let's say, 300, and here you had, let's say this was 300, 500. Okay, so this coordinate was 300, 500. Now this 300, 500 is here, okay, but if you project this here, this is not going to be 300, 500, because the size is only 60, 40. So you cannot just project it like that. Okay, so here it was 300, 500, here also I'll place it as 300, 500. That is not possible. Okay, so you need to get that out of your head. So since the sizes are different, what you have to do, the very first thing basically is, you have to find the subsampling ratio. So you might remember this. What happens is, see, suppose you have a big image and you have a small image. Okay, so the dimension ratios are similar. So in that case, what you do is, if suppose this is let's say 300 cross 600. Okay, so this is the size, and here what you have, the size is as 100 comma 200. So in that case, what you can say is, see, so what is the subsampling ratio? It is 1/3. So that means if you multiply this thrice, it will come to this. Or what that means is, if suppose here I have a value of, let's say, 99, so a point is here which is in 99, the x value is 99. Okay, so in that case, what will happen here is, it will not be 99 again, because 99 is way low here, so it will not be 99. In that case, what it will be is, it will be 33. Okay, now you understand the thing. So if you have, you are projecting this here, this is a smaller thing, however this is a smaller part of this whole thing only. So you need to find the very first thing, which is the subsampling ratio. So what is basically the subsampling ratio? Now the subsampling ratio is feature map size divided by original size. So this is how you get your subsampling ratio. Okay, so if your subsampling ratio for your length is, in this case, see, you had your width, your length only, yeah, 600 here, and here you have 40. So your subsampling ratio will be basically, for the length, 40 by 600. Okay, and in this way, what you will do is, you will find the subsampling ratios for all these, and once you have these values, now you can project it here. One more time, let me explain this. Here, let's go back. This is 300 comma 600. Okay, this is the whole size of your original image, and here the size is 100 cross 200. Let's say here I have 99 comma 120. Okay, so suppose this is a point here in the original image, which is in 99 comma 120. So the very first thing I will do is, I will find the subsampling ratio. My subsampling ratio in this case is 1/3. See, 100 by 300 and 200 by 600, this comes out to 1/3. So my subsampling ratio is 1/3. Now this is 99 comma 120. So what I'll do is, I'll multiply this by 99, 1/3 with 99 and 1/3 with 120, and find the point here. So this will come out to be 33 comma 40. So my point, which is in the original image at 99 comma 120, is now at 33 comma 40. So what is happening is, basically, see, Okay, so here you have the image, and suppose you find the coordinate here. So all these 4 coordinates in this manner, in the value, the way we were finding out using subsampling ratio, in the same way all these bounding boxes, these region proposals, can be somehow projected into this ROI using subsampling ratio. You understand this? So what is happening is basically the whole thing, the ratio of the whole thing remains the same, right? But the size gets smaller. So if suppose, again let's go back here, and the subsampling ratio, let us suppose it is 1 by 3 again, and this is 99 comma 120, my x coordinate for the leftmost corner. Okay, so for the top leftmost corner of my first bounding box, this is 99 comma 120. In that case, here suppose the sampling ratio is 1 by 3. Okay, I am just assuming it, so do not take it seriously, but yeah, so it is 33 comma 40. So in that case, this position comes here. So in the same way, you can find the coordinates for all the 4 boxes, and you can find the coordinates for all the 2000 region proposals, or whatever number of region proposals you are using. In fast RCNN, the number of region proposals are way less than 2000. Okay, so the n region proposals you can decide for yourself, and in that way you will project the whole thing here. So you now understand about region proposal projecting. So now you have feature maps in which the bounding box have been projected, and all this can be done without even having to take so much of problems, because see, earlier what we were doing is we were passing the image, and every time we were getting a region proposal, we were passing it through VGG16. So one of the problems that was happening was, see, when you were warping the image, so if you have a human image, okay, and if you warp it out so that it actually fits this whole network, CNN network, so in that case what happens is your image gets distorted. So that is the problem with, suppose, let's say I'm saying, so this is kind of a rectangular box, right? This is the image, this is a rectangular box, selective region proposal. Now I have to change this to 227 cross 227. In that case, what will happen is it will become more of a square box. So the shape of the actual region proposal gets distorted. So that is also one problem that was happening. And the second problem was passing all the 2000 region proposals one by one through VGG16, when actually you can, when all those region proposals together form one image, and you can just pass the one image there, and on the feature maps you can project the region proposals. All right, so this is the first step that we did, that is finding the subsampling ratio, and once you have the subsampling ratio, you have to project the image into the feature map. Okay, sorry, the bounding boxes into the feature map. So my first step is over. So my next step is basically, my second step is basically ROI pooling. So what is that? See, here once you get these region proposals, again you have to see the sizes are different. So this is more of a rectangular in this format, this is rectangular in this format. Obviously the two sizes are different, but you have to pass the whole thing through fully connected layers. So you have to flatten this out, whatever you are getting, and you have to pass this through fully connected layers. Now if you flatten this out, this will give a different value, this will give a different value. So that is one problem. When we had RCNN, we were not having this problem. Why were we not having this problem? See, what was happening was, we were here, when we were getting the image, we were changing the shape here and passing it through CNN. Once you pass them through CNN, all the feature maps are of the same size. So we were not having any problem, but now we are having this problem because we are not using the warped images and getting the feature maps from them. We are projecting the feature maps from the selective search into directly the feature maps itself. Okay, so the projecting of the bounding boxes from the region proposals into the feature map itself. Okay, this was the one that we are doing. So we are still having the problem that the sizes are different. So to solve this different sizes thing, what we will be doing is ROI pooling. So hence you have this known as ROI pooling. So let us say this is your feature map. Okay, so this is your input, your feature map. This here is your region proposal. So you did the subsampling ratio and you found out this is your region proposal. So this is of a particular shape, but for your fully connected layers you do not want this shape. You want some suppose let's say 4 yeah, four, sorry, 1 cross 4 vector, suppose, all right, and you have this particular shape. So how are you going to get that? Or for your feature maps, or your flattening out, before flattening out you want a shape of 2 cross 2. So you want this shape, but you have the region proposal of this shape. Okay, so despite any size, I am saying this again, despite any size, let's say I have this size, even then I will be able to change this into the particular size that I require using ROI pooling. So ROI pooling stands for region of interest pooling. Okay, so let us get back here. So you have this as your region proposal, but after flattening out and everything, you want this particular size. Now this size cannot come back to this size, so you have to do something about it. So you want 2 cross 2 as your image after from the region proposal, but you have this particular size. So what you will do in that case is, first, what is the size of this? So this is 8 cross 8. Okay, so okay, this is 7, this is 5 cross 7, I'm sorry. So this is 5 cross 7 region proposal size, but you want your final feature map to be of 2 cross 2 size. So all your feature maps, despite any size, can be converted in this particular size. How can you do that? Before we go and understand this, let me explain you with a more simpler example. So suppose you have an ROI region proposal that is 8 cross 8. You want a 2 cross 2 as your final feature map. Only then can you be able to pass it through a fully connected layer. So in that case, what you will do is, you will do max pooling. How will you do max pooling? So what you will do is, first, for to get a 2 cross 2 image, you will divide this actual by 2 cross 2. So you will get 4 cross 4. So that means if you have an 8 cross 8, suppose, whatever, let us suppose this is an 8 cross 8. Okay, so in that case, what you will do is, you will take 4 cross 4 regions. So you have this 4 and you have this 4 here. So you will take this region and you will do a max pooling here. Then you will take another 4 cross 4 region and you will do a max pooling there and there and there and so on. Now let us get into this example. So you have a 5 cross 7 as your region proposal, but you want a 2 cross 2. In that case, what you will do is, you will basically divide 5 and 7 by 2. So in that case, what will you get? You will get a 2 and a 3. So that means you will get a region proposal where you have 2 and 3, and in the same way you will divide it. So you have a 2 cross 3 and the remaining becomes one region. In the same way here you will have, since you have already taken 3 here, so that means you have a 2 cross 4 here and you get another region proposal. So basically, after dividing, you get your size of the regions. Once you have the size of the regions, the very next thing that you will be doing is now getting the maximum values from here, a max pooling from these boxes. So here, what is the highest one? 0.85. So 0.85. Here, what is your max pooling value? 0.84. So you get 0.84. Here, what you have the max pooling value as? 0.96. So you get 0.96 here. And finally, here what you have? You have 0.97. So this is the image, you got the region proposal. Once you get the region proposal, now you will be doing is ROI pooling. How will you do the ROI pooling? You have the actual values that you require for your feature map sizes, and you have the values for the region proposals. You will divide the actual values with the region proposal values, and you will get the values of each box. Once you have the values of each box, you will do max pooling for each of the boxes, and you will get the final layer. Now this is your final feature map. So this is known as ROI pooling, region of interest pooling. Okay, so let us go back here and let us now understand the whole thing. Okay, so let us understand this again one more time. So you have the image, you pass this to a CNN network. Once you pass this through a CNN network, you get all your feature maps. At the same time you have the image, you pass this through a region proposal network, that is your selective search in this case. Once you have your selective search, you get all your regions. Now you cannot directly add the region coordinates into your feature maps. In that case, you have to project this. To project this, what will you be needing? You will be needing a subsampling ratio. So how do you get the subsampling ratio? Using feature map size divided by original size. Now you have the subsampling ratio. Once you have the subsampling ratios, now you can project these regions into your feature maps. Now the feature map regions have been projected. Now what you will do is, see, the problem is these feature map sizes, these region proposed will have different sizes, but to make it into a fully connected layer, you need feature maps of the same size. So in that case, what we will do is ROI pooling. So what is region of interest pooling? Region of interest pooling is, suppose you have a region and you want a particular size. So what you will do is, from the actual size that you have, you will divide it with the size that you require. Once that comes out, you get the values. Now what you will do is, you will divide the region based on these values. Okay. So now that you have divided these regions, so you have 2, 3 here that comes out. So what you will do is, you will make a 2, 3 box. The remaining becomes 1 box. So the main thing is basically divide your length, which is 5, into 2 areas. The first will be of 2 pixels. So you have divided this, and then you will, what you will do is basically you will divide your now width, which is 7, into 2 areas. So the first area will be 3. So you divide it into 3 and the rest becomes 1. Alright. So now you have these boxes. What you will do is basically you will do max pooling and get the maximum values, and finally you get your feature map of the desired size. So despite the size of the image, again I am saying despite the size of the image, you can still get the value that you require using what is known as ROI pooling. Let us take another example. Let us take a simple example here. Okay. So I have this, suppose, as a region proposal. So this is what size? This is 4 cross 4, right? So in that case, what I will do is I will divide this by 2. So now since my height is 4 and I have divided it by 2, so that means the whole thing so the value is 2. So that means I will divide this height into 2. In the same way, I will divide my width into 2 as well, and I get the 4 boxes that were required, or any number of boxes. And once you have the box, what you will do is you will basically do ROI pooling all over again. So max pooling you will do, and you will get the values. Let us take one more example. The reason why I am doing this so many times is so that you understand. Let us say we have now this time a 3 cross 4 region proposal. Okay, so you have a 3 cross 4, you will divide it with a 2 cross 2. So you get 1 here and then you get a 2 here. So 3 is basically your length. So that means you will divide this with so your box will be first of 1 size, because you have divided 3 with 2 and 3 is your height. So you have this as 1. Now you have divided this height into the pixel box. So you have the size of the pixel box is 1, and in the second time you will divide it with, since this is 4, your width is 4, so you will divide it with 2, which is the actual feature map size that you require, and you will get the value 2. So you will now divide this into 2, the width into 2 pixels. So now you have all your 4 regions, and you can again do your max pooling. So now you get all these. Now since the feature maps are all of the similar sizes, you will pass this through 2 4096 units. Okay, first fully connected layer and second fully connected layer. Once you have passed this through it, what you will do is you will then again pass it, divide it into 2 different networks or 2 different models. The first model will be a classification model, second will be a regression model. Regression model is basically used so that you can better, or you can make your coordinates better that you got from your selective search region. Okay, so that is what you will be doing here, and here you have basically a classification task. By the way, here your activation will be softmax, since this is a classification task, and you will have k plus 1 classes, like I said, where k is the number of classes and 1 is to signify your background. So now finally that we have done all of this, let us come to the final part, that is the loss part. So how will a loss look like? So our loss is basically, it's not the normal losses that we have, it is the loss of the class that you are getting and the loss of the location that you are getting. So it is an addition of both. So loss of class is basically, loss of class is basically probability of u. Okay, so this is basically log loss here, log of class, loss of class, and log of loss of location is basically L1 smooth L1 loss. So that means basically if it is 0.5 x square, if mod of x is less than 1, and x minus 0.5 if not else. So this is basically L1 loss, smooth L1 loss, and here you have log loss, and the summation of both these losses will give you the actual final loss. So the L1 smooth loss that you will be getting from this regression part of the model, and the log loss you will be getting is from this classification part of the model. Now do you understand the whole thing? Again, so you have the image, you pass it through a CNN network, a backbone CNN network, and you get the feature maps. You project the feature maps on the feature maps, the region proposals that you get from selective search. Once you have projected it, what you will do is, the feature map sizes are different, so the next thing you will be doing is an ROI pooling, and you get all the feature maps into the same sizes. Now you can pass it through fully connected layers, 2 fully connected layers, and then you have, again it is divided into 2 different networks. The first network basically is for classification, the second is for regression, and the loss is finally the loss that you get from classification plus the loss that you get from regression. Alright, so that is the whole thing about fast RCNN. It gives a better MAP compared to RCNN, plus it is 146 times faster. So that is the whole thing that we had about RCNN, fast RCNN, I'm sorry. So that is it. I hope you enjoyed the class and keep learning.